Hi there, my name is Samer Nuruddin, and I'm excited to present my joint work with Trevor Brothers, Lin Wang, Michael Spratling, and Gina Cooperberg. The key goal of this project was to explore the extent to which predictive coding and neural process theory can explain aspects of the N400 event-related potential. As a quick reminder, the N400 is elicited in response to any meaningful stimulus. For example, when we time block to the visual presentation of a word in a sentence, you might get the following ERP plot on the right. On the x-axis is the time in milliseconds, and on the y-axis is the voltage in microvolts, with negative plotted up. Now I want to draw your attention to the N400 peak here. Its latency is fairly constant, at around 400 milliseconds, but its amplitude typically reflects the difficulty of accessing the semantic features of that word. Now this particular ERP illustrates the effect of word predictability. Words that are predictable in sentence context are easier to process, which is reflected in a smaller amplitude N400 compared to less predictable words. It's been somewhat difficult to map the N400 onto traditional psycholinguistic constructs such as lexical access and integration. But recently there's been some kind of consensus that the N400 reflects the impact a given stimulus has on the current state of semantic memory, which itself is influenced by the context in which the stimulus occurs. And conceptualizing things this way makes many phenomena intuitive. So, running with the previous example, consider word predictability. If you read a sentence like "he mailed the letter without a stamp," where the final word is entirely predictable given the context, the word stamp is expected to have less impact on semantic memory than if it were not predictable. Another example is semantic priming. So if you read the word doctor, a set of semantic features like hospital, medicine, and so on might be co-activated in semantic memory along the way. Now, because many of these medical semantic features are already active, reading a related word like nurse is expected to have a smaller impact on semantic memory than reading an unrelated word like dog. Similarly, if a word shares spelling with many other words, you can imagine that it will co-activate many more features than a word whose spelling is relatively unique. This implies that words with many orthographic neighbors are expected to impact semantic memory to a greater extent than words with few neighbors, which is consistent with the N400 data. So this framework is great because it can help us make sense of many phenomena. But there's still some work left to do, because it leaves many cognitive processes unspecified. So what we need at this stage are computational models that make it explicit how the bottom-up information is interacting with the state of semantic memory to generate these phenomena. And several such models have been developed. One class of models proposes that the N400 reflects the total semantic activation elicited by the input. Our model falls in the second class, which proposes that the N400 reflects the change in state elicited by the input. Most of the models that focus on the change in state implement the idea that there is a state of memory that's being impacted by successive bottom-up inputs. In some of these models, the researchers then go back and compute the difference between the new state induced by the new input and the previous state induced by the old input, and they operationalize this difference as the N400. So this can be thought of as an implicit prediction error. One problem with this approach, though, is that it's not clear why the model might want to compute this difference. And one possibility is that the difference, the N400, is just an epiphenomenon that comes out as a byproduct of other computations. But then we would need an account for what those other computations are, which this model doesn't provide. In another model, the N400 was framed as an explicit prediction error. In other words, it was computed as the difference between a prediction of what the next input will be and the true next input. But in this setting, the error was used only for post-hoc learning, and it played no online role in the processing of the stimulus. So to sum up, these models share the intuition that the N400 is reflecting some kind of prediction error, whether implicit or explicit. And what I want to present next is a framework that gives prediction error a central online role in stimulus processing. This framework is called Predictive Coding. So under predictive coding, the top-down connections in the cortex are thought to convey predictions, and the bottom-up connections convey prediction errors. Notice that this scheme reduces redundancy in the feed-forward signal. So rather than passing the full signal forward, neurons only need to pass the unpredicted part of the signal. So prediction error here is computed explicitly in the service of perceptual inference. Rao and Ballard first shows that interpreting feed-forward activity this way could explain, for example, why a neuron that optimally responds to a horizontal bar will stop responding when the horizontal bar extends beyond its receptive field. This is because the horizontal bar is now redundant with its context. And this approach was later extended to other phenomena in neuroscience where it's been largely successful. So here, we use the predictive coding architecture to explore the possibility that the N400 is reflecting the magnitude of lexicosemantic prediction error. And in the spirit of classic connectionism, we had units encoding the state at orthographic, lexical, and semantic levels. But what makes this a predictive coding architecture is that at each of these levels, we also had a separate population of error units encoding the difference in activity between these states and the predictions generated from the level above. So the idea is that each level would compute predictions of the activations below, and then get back a prediction error, instructing the state units on how to update their activations to generate a better prediction at the next cycle. However, the state's update is also forced to take top-down information into account, which keeps the system robust against a potentially noisy bottom-up input. And because this is a hierarchical system, the newly updated state is now the bottom-up input for the level above, where the same procedure repeats. So essentially, by doing this repeatedly over many cycles and attempting to minimize prediction error, the model eventually converges on a consistent representation at all levels in the hierarchy. Note that at the very top of the model, we included a dummy contextual layer that allowed us to pre-activate words before the onset of the bottom-up input, which was important for some of our simulations, as I'll describe later. So in the simulations that I'm about to show, we're going to be summing the activity in the lexical and semantic error units at each iteration of the algorithm and plotting the sum over time. Intuitively, we expect this lexicosemantic error to rise as the state units are being updated and to fall when the state units converge to the activations that explain their bottom-up input. Our key contribution is to show that the rise and fall of this error follows the N400 pattern remarkably well, across a wide range of simulations, which we turn to next. Our stimuli were 512 four-letter words that were represented in the model, and these varied on three uncorrelated dimensions. One dimension is the lexical frequency, which was coded into the feedback weights, so that the high-frequency words were assigned stronger feedback connections than low-frequency words. Another dimension on which our stimuli differed was concreteness, and this was coded as the number of semantic features associated with a word. Concrete words were assigned 18 features, and abstract words were assigned 9 features. And this is depicted here on the right. Although it's not shown here, some words shared semantic features, which allowed us to simulate effects of semantic relatedness. Finally, our stimuli also differed on the dimension of orthographic neighborhood density, which essentially indexes the number of words a given word's spelling is similar to. For example, a word like ball has more neighbors than a word like kiwi. To operationalize a given word's neighbor density, we computed the average edit distance between each word in the model's lexicon and its 20 closest neighbors also in the lexicon. The first simulation concerns the effect of lexical frequency on the N400. And as a reminder, frequency information was encoded in the feedback weights in our model. This means that when all else is kept equal, the model has a baseline bias to predict the more frequent words. So as a result, we expect it to require less error information to settle on an activation consistent with a higher frequency word. And indeed, this is what we find. In this and the rest of the simulations I'm going to show you, the x-axis represents the number of iterations that have passed since stimulus onset, and the y-axis represents the summed lexicosemantic error. The outcome measure we used for all of these simulations was the average lexicosemantic error in a 10 iteration window surrounding the peak. So here we can see that low-frequency words in black elicit a larger error than high-frequency words in red, which replicates the empirical finding on the left. Next, we turn to the concreteness simulation. So because concrete words activate a wider set of semantic features, we expect them to elicit more error. And again, this is what we find, which replicates the empirical finding on the left. Next, we turn to orthographic neighborhood size. In our model, words with dense neighborhoods like ball will temporarily activate a wide non-specific set of representations, resulting in large and non-specific error that take longer to recover from. On the other hand, words with sparse neighborhoods like kiwi will only activate representations that correspond to them, leading to smaller and more specific error activity. And indeed, this is what we see, which replicates the empirical finding on the left. In addition, we find that this effect is linear and continuous, which has also been shown in the literature. Next, I want to talk about the repetition priming simulation. So the procedure is simple. We presented a word for 2 iterations, followed by 2 iterations of blank inputs, followed by either the same word or an unrelated word. And what we find is that repeated targets elicit a significantly smaller error than unrepeated targets, which replicates the empirical finding here on the left. The semantic priming procedure was very similar to the repetition procedure. So for the primed condition, we presented 2 stimuli with 8 features in common. For example, sour followed by lime. For the unprimed condition, we presented the same target as the primed condition, but this was preceded by an unrelated stimulus that it shared no features with. So example, a word like bold. And we expect that when the target is preceded by a related prime, some of its features are already active, and it will require less error to converge. And again, this is what we find, which replicates the empirical finding that we see on the left. One strength of this model is that in addition to lexical effects, it can also explain sentence context effects. So the classical finding here on the right by Kutas and Hilliard is that words that are more predictable in sentence context, as operationalized by closed probability, will elicit a progressively smaller N400. In order to simulate the effects of word predictability, we gave top-down activation to the highest contextual level of our model. We clamped this to the desired closed probability distribution, and we let the model run for 20 iterations without any bottom-up input. Following this pre-activation phase, we then presented the actual bottom-up input. So for these simulations, during the top-down pre-activation phase, there are 4 levels of predictability, indicated here by the 4 superimposed lines. Then, on iteration 20, we presented the pre-activated bottom-up input. And replicating the empirical result, we found that words that were more predictable elicited a smaller error on average. But critically, the model doesn't show effects of prediction violation over and above closed probability, which is also consistent with the empirical results. So the goal in this simulation was to present an unexpected bottom-up input in either a high constraint or a low constraint context. So to do that, we pre-activated a given word either strongly or weakly for 20 iterations, and then we presented a different word. And what we find is that the error elicited by the unexpected word is equally large, independent of contextual constraint. For comparison, this was the error that was elicited when the expected word was presented. Finally, the model can also replicate the smaller N400 amplitude when the unexpected stimulus semantically overlaps with the predicted word. So to show this, we pre-activated a word like sour, and then presented either sour itself, or a semantically related word like lime, or an entirely unrelated word like ball. And as you can see, the resulting prediction error closely follows the ERP on the left. Although it's not shown here, we also found that the strength of this effect depends on the level of constraint, which also replicates the empirical result. So what I've shown is that this predictive coding framework can capture both the time course of the N400 and its functional sensitivity profile, both to lexical and to contextual factors. We didn't have the time to go over this, but it can also capture some interaction effects, indicated here by the arrows. In all the simulations so far, we're plotting the magnitude of prediction errors produced during perceptual inference. But at the same time, the internal states of the model are representing the relative level of activation for different lexical candidates. And so the framework also provides a method for simulating behavioral response times in tasks like lexical decision and naming. So this is a natural next step because all of the manipulations that we studied here have behavioral counterparts. And critically, some of these factors like concreteness produce paradoxical effects like larger neural responses but faster response times. So testing behavioral output would provide a particularly stringent test of the model. So to sum up, predictive coding can capture the time course and functional sensitivity profile of the N400, and it can do this within a simple and interpretable framework that has an explicit computational role for prediction error in language. Outside of language, this framework has been used to capture phenomena in vision and auditory neuroscience, which lends credibility to the idea that similar processes might be happening in language. In addition, the computations in predictive coding have been proposed to map onto a cortical circuit, which is very encouraging from the point of view of neurobiological plausibility. So, taken together, these properties make this a remarkably powerful framework for understanding the neurobiology of language. I want to thank my lab at Tufts and our collaborator Michael Spratling at King's College London for all their valuable contributions. And thank you all for listening. I'm happy to take questions.